We start today chapter 4 on page 157 about summarizing bivariate data. So in the last three chapters we were dealing with mostly with data sets with one variable. In one variable, for example, we were dealing with a collection of values, and then we were able to get graphical summaries for univariate data like this one. Basically were histograms, the most important one. Then we also were able to get numerical summaries. So for example, the mean, the standard deviation, the z-score, and so on. So those were the two things that we did with univariate data. Univariate data, one variable. Now we're going to have bivariate data. So now we have two variables. And we're going to see those two variables usually as a table. So we're going to have a t table with values of x and values of y. Now we're going to do the same thing that we did before. So we need to generate some graphical summaries. Graphical summaries. And we're going to generate also numerical summaries. So that's what we will cover in this chapter. So we're going to work on two sections during this lecture, and then we're going to be able to have these summaries of bivariate data. So the first thing that we're going to work on is on a scatter plot, but let me just write, we're going to start section 4.1. Section 4.1 on page 158, and this section is just about correlation. I would say that it's going to be linear correlation, what we're going to look for in this section. So we have order pairs. So these are order pairs. So order matters. So, and we're going to use then for our graphical summaries, we're going to use scatter plots. So the first thing that we're going to see is scatter plots, because they're going to give us a clue about whether the data values follow a linear pattern. So the scatter plot is just a plot of the points of the order pairs on a Cartesian coordinate system, a rectangular coordinate system. So we're going to have every pair of values that you're going to have here, x1, y1, are going to be plotted as points with coordinates x1 and y1 somewhere here. And then we have another value, x2, y2, which is going to give us a point with coordinates x2 and y2, and you're going to put the point somewhere. And then you continue doing the same thing with the rest of the pairs that we have here. So this is going to be our scatter plot, and the idea or the purpose of doing this is that we are trying to find, so we are trying to find whether the points follow a linear pattern. So this is the important part. We want to know whether these points follow a linear pattern. So let's see the kinds of plots that we might find. So we might have, and we don't expect to get the perfect straight lines, but something that is close to. So you might have points obtained in this way. So this is going to be a positive linear pattern, a positive linear pattern. So the line goes up when you go to the right. You might have the opposite. You might have points that might look that they are following a negative linear pattern. So this is going to be a negative linear pattern. So the points follow this behavior. So we might have also points like this. You might think that this is a linear pattern. Some people might think that it's not. So we can say that this is a weak linear pattern. Also, we can have points that seem not to follow a linear pattern. So you can see that they are like following a curve. So this is a positive non-linear pattern. So we can have also the opposite of this one. So something like this. So you can see that it's not linear. That is actually that the points are following a curve. So in this case, it's a negative non-linear. Negative non-linear. Because the values are decreasing. In this case, the values are increasing as you move to the right. And you might have something like not being able to identify any pattern at all. So the points are scattered over the entire region. So you can say that this is no linear pattern. There is no linear pattern, and there is no non-linear pattern like this one that is a curve. But the only ones that we are looking for are the linear patterns. So the first two, that's what we want. So we're going to use then a function in R to find that out. So for our scatter plots in R, scatter plots in R, we need to enter the X values and the Y values in the same way that we have been doing that for any variable. Then a simple command. You're going to plot X and Y. You're going to plot the order pairs X, Y. So, and once you get the plot, then you're going to try to identify whether you see a linear pattern or not. Okay. Our problem is, this is what that we do when we are trying to get a graphical summary. Now, for a numerical summary, we're going to use, so this is the graphical. This is going to be our graphical summary of bivariate data. For a numerical summary of bivariate data, we're going to find use a statistic R, or a parameter if you are working with a population rho. So remember, we use Greek letters for parameters or English letters for statistics. So a statistic comes from a sample, a parameter comes from a population. So, and we call this statistic or parameter, this numerical value this is going to be the correlation coefficient. The correlation coefficient. So, and you're going to find that information about the correlation coefficient on page 160. So this is on page 160. So this is going to be one of our first numerical values that we're going to use to tell whether the variables x and y follow a linear pattern. So what are the steps to find the correlation coefficient? I just summarize the steps here. So we're going to start computing numerical summaries from our data sets. So we're going to get the mean of x, the mean of the y values. We're going to get the standard deviation of x, the standard deviation of y. That's the first step. Then we're going to compute the z-scores for x and y. I'm just writing here the formula that we're going to use in R to do that. But this formula comes from the formula that we learned in the last chapter about the z-score. So the z-score is just x minus the mean over the standard deviation of x, and the z-score for y is going to be just the value y minus the mean of the y's over the standard deviation of y. So once you get the z-scores, the correlation coefficient R is going to be obtained by adding the product of the z-scores and divided by n minus 1. So R is just the sum of the product of the z-scores, zx and zy, and we're going to divide this by n minus 1, where n is just the number of data values, it's just the size of the sample. Then we're going to use R squared to know the fraction of the variable y that is explained by the variable x. So R squared is going to be a percentage of the values that you have for your response. Usually y is going to be the response, and x is going to be the explanatory variable. So we are trying to understand y as a function of x. We are trying to know how y behaves by knowing how x behaves. So we are trying to see whether we can write a linear equation, y hat equals mx plus b. You are familiar with this formula, the equation of the line. So we're trying to find whether the values x and y that are given initially are following a linear pattern, and if they are following a linear pattern, then we're going to be able to find the equation of that line. So what is important to say at this point is that we are going to say just by looking at the scatter plot and checking the value of R, whether there is the possibility that there is a linear pattern, but to have some certainty on those assumptions, we need to conduct a hypothesis test. And so we're going to come back to this linear correlation and this equation of the line when we cover chapter 13. That's the chapter where we're going to have for sure whether a group of points, ordered pairs, are following a linear pattern. In this chapter, it's going to be just the possibility, oh, I think R equals 0.7 and 0.8. Maybe there's a linear pattern. Or we can look at the scatter plot, but there is uncertainty on what we are saying. Until we cover chapter 13, we're going to have some degree of certainty about a data set, a bivariate data set following a linear pattern. So I think the next thing that we're going to do is just we're going to solve an example, and then you're going to play with this new tool, the scatter plot and the linear correlation coefficient, and then we're going to move on to obtaining the equation of the line on section 4.2. So let's start with example 4.1. Example 4.1 on page 159. So this example is about constructing. So we're going to construct a scatter plot for the data in table 4.1, which is on page 158. So let's check this this information. So we can have here the problem first. So it's just constructing a scatter plot. So you can see here, when I construct a scatter plot for the data in table 4.1, and you can see here the scatter plot that your book shows. So we're gonna try to get a similar scatter plot. You can see now the points here on the plane, and you can say, oh, it seems that these points are following a linear pattern. So let's then let me show you the table where we're gonna that we're gonna use to work on this problem. So table 4.1 is the size and the selling price for a sample of houses. So we have here as the size of a house in square feet and the selling price in thousands of dollars. So for example, a house with a 21 square feet, 2,500 feet, was sold in around $400,000. Then a house with a 55 square feet was sold in $426,000, and so on. So we have 1, 2, 3, 4, 5, 6, 7, 8 houses, and their prices. So we want to know whether it's a linear pattern that this data might follow, because if that is the case, then we're going to be able to predict the value of a house just if we know the size of the house in square feet. So for example, a house that is like maybe 2,900 square feet, what would be the price? So there is no house here with 2,500 square feet. So you might say maybe between 435 or 469. We don't know. We need to put these values on a graph first, then we need to get an equation, and only then we're going to be able to predict the value of a house given its size. So this is the problem that we're going to solve now. So let me just continue. So we're going to enter the values for first the sizes of those houses. So first we're going to have an X, which is the size of the house, and then we're going to enter all those values: 2521, 2525, until we get the last one, 3198. And the same thing, we're going to enter the values for prices. So I'm going to give the variable y for this to enter these values. So the first one was 400,000. We are just getting rid of the thousand part, just entering values in thousands. So we have 426, then 428, and so on until the last one that we get, that is 455. So we have our data set. So now we're gonna just follow the recipe that I just mentioned. We're gonna use R to get first the scatter plot. So we're gonna do plot X and Y. So let's do that. Let me show you our console first. Okay, we have the R console. Now we're going to enter the values. Okay, let's start entering those values. So I'm entering X, I'm entering Y, I'm also entering N, the size of the sample, which is just 8 houses. And then we're gonna start getting our first thing is the scatter plot. So we're gonna enter plot X and Y. So we get the scatter plot now. So we have that scatter plot, and we have also the scatter plot that was obtained by the software that was used by the author of our book. So you can compare that scatter plot with the one that is on page 159. So that was the scatter plot, very similar to the one that we just obtained by using R. So that's the first problem, nothing difficult to work on. So now we're going to work another example, because that was the graphical summary. Now we need the numerical summary. So we're going to work now example 4.2 is on page 161. So let's see what is that problem about. So 161. So on page 161 you have the formula for the correlation coefficient. You can see that it's a huge formula. So this formula is written in terms of x bar, which is the mean of x, y, and y bar, which is the mean of y, and the standard deviation of x, the standard deviation of y. So the formula in this way looks like a very difficult or complicated formula to handle. But you can see that this parenthesis is the z-score for x, and this parenthesis is the z-score for y. So that's the reason I prefer finding the z-scores first and then finding the linear correlation coefficient R. So there are values that this coefficient is going to obtain. The values that this coefficient might obtain are values from -1 to +1. So if the values are close to 1 or close to -1, then we have a good linear correlation. If the values are close to 0, that means no linear correlation at all. So that's what we need to learn. So let's go now and work on example 4.2. So we're going to use the same table 4.1, to compute the correlation between the size and the selling price of the houses that are in that table. So now our problem is just finding the z-scores and then finding R. So what we're going to do here is that we're going to find Zx is going to be just any value that we entered previously, x, minus the mean. So we need the mean. So you can use the formula mean of x, and we're going to divide by the standard deviation of x. And zy is going to be just y minus the mean of y, and we're going to divide that by the standard deviation of y. And then we're going to get the sum of the product of zx and zy, and we're going to divide that by n minus 1, and that is going to be the linear correlation coefficient. So let's do that now. Let me go and back to my R console. So now I'm going to enter those formulas. The zx is just x minus the mean of x divided by the standard deviation of x, and zy is going to be y minus the mean of y divided by the standard deviation of y. Well, then the sum of the products of the z-scores divided by n minus 1, where n is just 8 houses, is going to give me the linear correlation coefficient R is 0.9005 and 918. So it's pretty close to 1. So that means that what we were looking before was a line that was ascending. So, and also if you square this, so if we write 0.9005918 square, we get R square is 0.8110657, which indicates that 81.11% of the y values are perfectly explained by the x values. So that is the meaning of R squared. It's going to give us the percentage of values. So I'm just wrote here R, then R squared, and then you multiply R squared by 100. So in that way you get this value in a percentage form, and indicating that 81% of the y's are explained by the x's. So that's the meaning of this. So 81% of y is explained by x. So now it's going to be your turn to work some problems from the corresponding exercise set. I'm going to give you two problems, and then we're gonna continue with the next section, and we're gonna finish the lecture. So you're gonna go and open your book on section 4.1 to see the exercise set. This is on page 167, and you're gonna solve problem 32, part A, part B, and you're gonna solve problem 34, part A, and part B. So I'm going to show you the problems, and then I'm going to give you a break for you to work on those problems. So let's see, problem 32 first. So 32 is on page 167. 167. So let's see, 38. So you're gonna need these data sets. You have information from 2006 and 2016. So you have two data sets, one for X, one for Y. So X is gonna be values from 2006, and Y are gonna be the values from 2016. So this is budget for selected organizations that receive US government funding for arts and culture. So what are the questions? The questions are the following. There are many questions, so you're going to work only part A and part B. Part A is just constructing a scatter plot, and part B, you're going to compute the correlation coefficient between the funding and in those 2 years. So that's what you're going to work on. Then the next problem is problem 34. So problem 34 is about carbon footprint. So carbon dioxide is produced by burning fossil fuels such as oil and natural gas, and has been connected to global warming. So there are going to be just a table presenting average amounts in metric tons of CO2 emissions for the years 1997 and 2013 per person. So there are going to be a lot of years. So we have the year, and we have the carbon dioxide for countries that are not the US, and also carbon dioxide from the United States. That's the second column. So this column is going to be your X, and this column is going to be your Y. So enter those information, those values, and you're going to construct a scatter plot again, part A, and part B is going to be just the correlation coefficient. So with part A, you get the graphical summary. With part B, you get the numerical summary for that bivariate data set. So now we're going to continue with the second part of this lecture, which is just once you know that data set in two variables is following a linear pattern, then you want to know the equation that describes that linear pattern. So we're going to cover now section 4.2. This section is the least squares regression line. So that's the fancy name for the equation of a line. So usually we are more familiar with the equation y equals mx plus b. We learned that in algebra, in our algebra classes, that this is the equation of a line, the equation of a line or a linear equation. So we have a data set with values of x and y. So we get a graphical summary, which is just a scatter plot. So we did that on the last section, and then we get a numerical summary. A numerical summary is going to be numerical values that we're going to use to describe the data set. So the first one was the correlation coefficient R if you're using a sample, or rho if you're using a population. And there are more numerical values that we're going to use to describe that data set. So these are two more values that we're going to include. Two more values to be included in the numerical summary. So those values are going to be m, which is usually the slope of the line. So if you have a line here, so m is going to be related to the inclination of the line, the slope. So the slope, and b is going to be the intersection, the y-intercept. So it's going to be the intersection of the line with the y-axis. So this is going to be b, the y-intercept. That's what we learn in our algebra classes. When you are working with the line in statistics, usually we're going to change a little bit the notation. So we're going to use first y hat, because we're going to say that this is a predicted value of y, a predicted value of y, the value that we observe, the response. Remember, y is the response. Y is the response. And this is going to be a function of v0 or v naught plus v1x. So in statistics, we reverse the way that these values and these terms are written. So we start with the y-intercept, and we call it v0, v sub 0, and then plus, and then the slope is v1 times x. So this is going to be the equation that we're going to obtain. So the formulas to obtain this equation are the following. So v1 is going to be obtained by using the correlation coefficient R, the one that we just obtained, and we're going to multiply that by the ratio between the standard deviation. So it's going to be the standard deviation of y over the standard deviation of x. So you multiply the ratio of standard deviations and the correlation coefficient, and then you're going to get the slope for the line. Then the y-intercept of v naught is going to be the mean of y minus v1, which is the slope of the line, times the mean of x. So that is going to be the formulas that we're going to use. So we're going to solve an example now. We're going to solve example 4.3. So we're going to work two more examples to finish this lecture. So example 4.3 is on page, let me see, example 4.3 is on page, what page is example 4.3? Okay. It's on page 172. Let me show you. It's on top of this page. That's the reason I didn't find it very easily. So we're going to use the data in table 4.2 to compute the least squares regression line for predicting price from size. So they are talking about the same data set that we used before, the data set that contain the prices of houses based on the square feet of those houses, the size of those houses. So now we're going to continue with the process. We obtain the scatter plot first and then the correlation coefficient, which was 0.9. And now we want the equation because we want to predict values of houses based on their sizes. So if you remember, this is the table that has the sizes and the prices. And then we were able to get the scatter plot. The scatter plot is just the points. And now we want to know the equation of the best line that describes this data. So you can suggest many lines. So for example, this is one line that is suggested to describe these data points. And you might have another line like this one, and you can say, oh, this line describes this point, and you're going to see that this line is not describing this point because the differences between the y's, the predicted y's are the ones that are on the line, are very, very, very far away from the observed values of y. So these vertical distances are the differences between the predicted value that you're going to get from the line and the actual value that was observed. So the actual response. So the difference of prices, in other words, because the y-axis is for prices, so any vertical difference is a difference in price. So you can see that this line is getting a lot of discrepancies for the prices that you observe from the real estate market and the prices that the line is going to suggest. So this line is not worth it. However, this line, you can see that the predicted values, the prices that you're going to get with the line are going to be close enough to the values that we observe, to the extent that then you can use the line to predict the values of houses for other different sizes that were not observed. So that's the purpose of trying to get the equation of a line. So let's finish this problem then. So we have example 4.3. I'm going to write just what we're going to do. We're going to use the data in table 4.2. Let me just give you to compute the least squares regression line. So that's the name, the fancy or the mathematical statistical name for the equation of a line for predicting price from size. Price from size. So we have our table. So we have size in square feet, we have price in thousands of dollars. This is square feet. And we have the values. that we already entered into our console when we created the histogram. So that's what we have. Now, what is the next step? So I'm going to just rewrite the first steps just in case that you were starting this program from scratch. So you need to enter the values for x, so separated by commas, and then you enter the values for y by using the lowercase c, parentheses, and then again the value separated by commas. Then we enter the number of data values. Check when you are solving the problems that I'm going to assign you that you need to change this value. Then remember we computed the z-scores for x and the z-scores for y. I'm just repeating the formulas to have them in a single place. So now you're going to have everything to solve a problem on linear regression on a single page. So then we're going to compute R. Now I'm going to give the name R to the sum of the products of the z-scores of x and y divided by n minus 1. So I'm now using a variable with name R because I'm going to use it to compute the mean and the standard deviation. So sorry, to compute the slope and the y-intercept. So the slope v1 is going to be r times the standard deviation of y divided by the standard deviation of x, and then the y-intercept v0 is going to be the mean of y minus v1 times the mean of x, and then you call these values. I'm going to show you how to call. You just enter v0, enter v1, and then you're gonna get the value. So let's work on this problem to get the equation of the line. So I'm going to use R. I'm going to go back to my R console. So let's see, my R console is here for you to see it. So I have the steps there, x, y, zx, zy, and I have R. I need to enter this step, and I'm going to add R equals, because now I need that value to be able to compute the mean, to compute the slope, which is v1 is going to be just R times the standard deviation of y divided by standard deviation of x, and you can just call v1 and you get 0.09. So that is going to be the slope. The slope is 0.09919795. And now v0, which is the y-intercept, is the mean of y minus v1 that I just obtained, that multiplies the mean of x, and I'm going to call it v0 is 160.1939. So I have now the information to write the equation of the line. So now we're going to be able to write y hat is going to be v0 160.1939 plus v1, which is 0.0991 times x. So this is the size of the house, and this is going to be the predicted price of the house. and this is the least squares regression line. So this is the least squares regression line, and you can add somewhere the value for R. You're gonna just get it just for the people to know how accurate or how good is your line fitting the values from the real estate market. So that's the part that you need to know to get the question of a line. Now you're gonna solve a couple of problems, and they're gonna get the final part by predicting some values. Oh no, let me finish with another example before giving you more work. So I'm going to solve example 4.4. So let's solve example 4.4. We're going to use the equation of the line to predict some prices. So example 4.4 is on page, what page is 4.4? Okay, 4.4 is on page 174. So we're going to use now the least square regression line for prediction. So let's work on this example, and then you're gonna have everything that you need to work on this one. So you're gonna use the least square regression line computed in example 4.3 to predict the selling price of a house of size 2800 square feet. So that's the problem. So we're gonna write part of the let's write, we're gonna use the least squares regression line computed in example 4.3 to predict the selling price of a house of size 2800 square feet. So what is the equation? The equation is y hat equals 160.1939 plus 0.0991 x. So this is the predicted price, predicted selling price, and this is the size of the house. So now we have x, they are giving you a value of x equals 2800 square feet. So y hat is going to be just 160.1939 plus 0.0991 times 2800. So we're going to use R to compute this value. So let's see. Let's go back to R for a minute. And let's finish this plan. So I'm going to have other way to do this is just V0 plus V1 times 2800. So it's going to be y hat is going to be 47.9482, but be careful, this is in thousands, so you need to report $437,948.2 for the selling price of the house. So remember, the data was given as the prices were given us in thousands of dollars. So you need to be careful with reporting just $437. That's not the price of the house, but if you multiply this by 1,000, then you get the selling price is the selling price for a 2,800 square foot house. So that's the problem. So now it's going to be time for you to work. So we have section 4.2 on page 179. We're going to work the exercise set. So there are going to be two problems for you to solve. Those problems are problem 22 and 24. This is just a continuation of the problems that you solved before about carbon dioxide footprint and something like that. So let me show you the problems. So first, 22 is about government funding. Problem 22 is here. So it's about government funding. So you already have these data sets, your X's and your Y's. So now you're going to compute the least square regression line. The least square regression line. Then you're going to have a question about two institutions having budgets that differ in $10 million in 2016, but how much would you predict their budgets to differ in 2016? And then part C is going to be the prediction of a budget given a budget in 2006, a prediction of a budget in 2016 based on values on 2006. So you can solve easily part A and part C. Try to read carefully part B. If you don't get it, send me an email and I can help you solve that part. So now, problem 24 is here. Is the carbon footprint for US and other countries during several years, 1997 through 2013. So you have the data set first. You already have this data set. So take a screenshot. Then you're going to compute the least square regression line. Then you're going to have a similar problem in part B that you're going to try to solve by yourself by reading the book. If you don't get it, send me an email and I can help you. And finally, part C is a prediction. You're going to predict the US emissions for a year when the non-US emissions level is 3.4.